Still not working, right?
En heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Gareth Banyard. Gareth Banyard has presented to the faculty his PhD thesis on the topic The Multiplicity of B-type stars in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy and astrophysics. He shall now publicly defend his PhD thesis. Gareth Banyard, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Gareth Banyard.
Thank you very much. And yeah, thank you so much everyone for coming today. I appreciate it so much. Yeah, I'll start the presentation. Today I'm going to be talking about my thesis, which the title is The Multiplicity of B-type stars. So I'll start with something relatable, hopefully, to most of you, which is the sun. And the sun is one of many stars in our universe, and to make things easier for ourselves, we like to put stars into categories. For example, we put the sun as a spectral type of G, but what exactly does this mean? Well, the spectrum of a star is stellar light that's being decomposed into its various constituent wavelengths. And we give stars spectral types based on the appearance of their spectra. And features in the spectrum of a star can indicate things like the chemical abundances present in that star, but also the temperature of the photosphere of that star, or the surface from which they radiate their photons to us. And so when we look at this, when we look at the spectrum of various stars, we can begin to think them into different spectral types. So we have this rather unhelpful alphabetical order of stars from the hottest O stars all the way down to the coolest M stars. It just so happens that temperatures correspond with masses of stars on the main sequence. And when we talk about stellar masses, we like to split them into three different categories. We have the massive stars, which are greater than 8 solar masses. We have the intermediate mass stars, which are between 1.5 and 8 solar masses. And we have the low mass stars, which our sun squarely sits in, and these are below 1.5 solar masses. So if we can infer the temperature of the star through its spectral appearance, then we also add another dimension to our observations. And on the y-axis, we can include the luminosity or the brightness of a star. On the x-axis, we can include the temperatures of these stars. And we end up with one of the most important diagrams in astronomy, the Russell diagram. And when we populate this diagram with many different stars, we'll begin to see that a lot of them cluster in this diagonal strip in the Russell diagram. And we call this the main sequence. And this is where stars are fusing hydrogen in their core into helium. And a star does this for 90% of its life, and this is why it is so populated. So if we know the temperature and the brightness of a star, we can begin to infer what kind of star it is, what kind of stellar mass it might have, and at what point in life it is as well. So that's an important thing to consider, is that stars are not static, they change throughout their life. And this depends also on what kind of gas the star has. So we need to consider this. And all stars form in nebulae, so clouds of gas. And these natal clouds of gas gravitationally collapse. Protostars begin to form, and they become hot and dense enough for hydrogen to start fusing into helium. And this, as I mentioned, is the main sequence. So if we look at low and intermediate mass stars, under 8 solar masses, they will stay on this main sequence for billions of years. And This will continue to happen until hydrogen in the core of the star will begin to deplete. You'll have a growing helium core surrounded by a burning hydrogen shell. And so the radiative force outwards in the star becomes weaker and weaker, and it eventually loses the battle against the gravitation of all of the material surrounding it in the star, and the core begins to contract. Once this happens, the envelope reacts by expanding, and we have a red giant. And then after this stage, as the core contracts furthermore, it can become hot and dense enough for helium to start burning as well. So when helium depletes in the core, we end up with a carbon-oxygen core surrounded by hydrogen and helium burning shells. This double shell burning is quite unstable, so we end up with extreme mass loss in what we call the asymptotic giant branch stage, which you don't see here, but it's just before the planetary nebula stage, where you can see that the entire envelope of the star has been ejected, and we get this spectacular object. In the center of this planetary nebula, you have a Kuhn carbon-oxygen dwarf, a Kuhn carbon-oxygen core, which we call a white dwarf. The life of massive stars, however, is quite different, and these need more energy to sustain the balance of their greater gravitational force inwards and their greater radiative force outwards. And because it requires more energy, it requires much more fuel, and we end up with stars that live for millions of years instead of billions of years, which is shorter, even though it doesn't sound factual. And quite like the red giant stage in lower mass stars, we end up with a giant stage in massive stars, but instead of being red giants, we get red supergiants, and these are the stars with most volume in our universe. After this happens, these stars burn, unlike lower mass stars, they can continue to burn consecutively heavier elements in their core until we reach an iron core. So we have, at the end of the massive star's life, an iron core surrounded by concentric rings of increasingly lighter elements outwards. When we get to iron, it's an endothermic process, and this means the star must stop here and core collapse happens. And as a result of the core collapse, we get, most of the time, a supernova explosion. What we get next in the final stage of these massive stars' lives depends on the remnant of that supernova. If it is over 2.1 solar masses, the star can continue to collapse in on itself into a singularity and we get a black hole. But if it's under 2.1 solar masses, it forms this very dense object called a neutron star. And you can also see that this process is quite cyclical. We get chemical and mechanical feedback both from planetary nebula and from supernovae, and they feed this into the next generation of stars. So just for a quick recap, we have massive stars where their masses are greater than 8 solar masses, and these are the progenitors of stars that will undergo core collapse towards the end of their life. This is what defines massive stars. And as a result, they are rare. And this is primarily because they are short-lived compared to low-mass stars, but also because star-forming regions have a tendency to form lower-mass stars over higher-mass stars. And we describe this with the initial mass function. Despite their fewer numbers than lower-mass stars, they dominate the energy budget of star-forming galaxies, and this is because of their strong stellar winds and their highly ionizing radiation. As for the intermediate mass stars, these are the progenitors of white dwarfs, and they are more numerous than massive stars, and they are important because they are the main producers of dust in our universe, and dust can affect everything from planet formation all the way through to the extinction of our observations. And also they are important chemical factories, particularly in the asymptotic giant branch stage, where, for example, they produce almost all of the lead and barium in the universe. Their difference from the low mass stars lies in their internal structure. So when we talk about the internal structure of stars, we want to talk about energy transport. And there are two main modes of energy transport. There's convective zones, where the bulk motion of gas transport energy from hot rising gas to cool sinking gas with this cyclical motion. And we have radiative zones, where the radiation of photons carries the energy out of the star. So in higher and intermediate mass stars, greater than 1.5 solar masses, we have a convective core and a radiative envelope. For stars like our Sun, we have a radiative core and a convective envelope. And for stars that are less than half the mass of our sun, we have a completely convective star. So, in this thesis, we're talking about B-type stars, and on the main sequence, they have masses between 3 and 17 solar masses. As such, they represent a transition between the intermediate mass stars in their subtypes of B3 through to B9, and the massive stars between B0 and B2. These are the early B-type stars. And they might not be the most massive stars in our universe, but under initial mass function considerations, they are the archetypal massive stars, and such they are the main progenitors of core-collapse supernovae and of particularly neutron stars. However, so far we've only talked about stars as if they're born, they live, and they die in complete isolation, but just like you and me, the life of a star can be greatly impacted in company. So, what can occur in nature is that stars can be gravitationally bound to each other. And when this happens, both of these stars orbit around a common center of mass. Furthermore, binary interactions in particularly closed systems can undergo the exchange of mass and angular momentum. And as I've described briefly, the mass of a star can greatly impact its evolutionary pathway. And so binary interaction can have a profound impact on its stellar evolution. To explore binary interaction, it's useful to look at the Roche model. So here we have two stars in the center, surrounded by these lines of gravitational equipotential. Along these lines, the gravitational force is equal at every point across the line. And around the two stars, you can see these two particularly bold lines, which form a peanut shape around the star, and this is called the Roche lobe. Any material within the Roche lobe should be gravitationally bound to that star. So with the Roche model, we can begin to describe different kinds of binaries. So we have detached binaries, where both stars in the binary system sit well within their Roche lobes, and as a result, no mass transfer happens between the two members of the star, unless, for example, we have strong stellar winds that carry material away outside of the Roche lobe. As we've seen, these stars are static, and they can change their volume throughout their lives. So what can happen is that the more massive star in a binary system will evolve first, it will expand, and it will begin to fill its Roche lobe. And when it does so, it deviates from spherical symmetry, and we get this teardrop-shaped star that begins transferring mass to its lower mass companion through the Lagrangian point L1, which you can see between the two stars. Then, if both of the stars in the binary system fill their Roche lobes, we end up with a contact line. And this is where both of the stars deviate greatly from their spherical symmetry. And in extreme cases, we can get over-contact binaries, where both of the stars overfill their Roche lobes, and as a result, they both share a common envelope of gas around the two stellar cores. They're also known as peanut stars. So, you might be asking, okay, does this matter? How often does this occur in nature? And here we have a general summary of several different types of time series observations using different techniques of observations, such as spectroscopy, long baseline interferometry, high cadence photometry of eclipsing binaries, and several other techniques that are all sensitive to different kinds of binaries, whether they're close or far away, or they have eccentric orbits. So this is designed to try and capture as many binaries as possible. And you can see that on the y-axis we have the companion fraction, which is how many stellar companions are expected per star of the primary mass of the primary star on the x-axis. So you can see that solar type stars on the left, in the red zone, are expected to have a companion fraction of 50%. And what this means is that we expect 50% of solar type stars to have a companion. But as you increase the primary mass, it appears that indeed there appears to be more companions per primary star, especially in the case of O-type binaries here, where you can see they're expected to have on average 2 companions per star. So you're expected the average O-type system to be in a triple system. So yes, it is frequent, especially as you increase the mass of the primary star, but do any of these stars actually talk to each other? Do they interact? Well, it turns out, in O-type binaries in particular, the configurations of them are such that a lot of them are close enough to interact during their lifetime. In fact, 70% of binaries are expected to undergo things like stellar mergers, envelope stripping, and accretion before they end up dying. So, yes, this seems to be something that will have a profound effect on the lives of binary stars, particularly for the massive stars. However, the constraints for the B-type stars are less robust. And this is important to know because we want to know the multiplicity properties of these stars so we can begin to predict things like core collapse supernovae rates, because, as I said before, they are the main progenitors of core collapse supernovae. And also they're the main producers of neutron stars. So if binary interactions can infect the stellar evolution of these stars, then it would be worthwhile to know whether they're in binary systems at all. And another product of B-type binaries is binary neutron stars. So we have two B-type stars, they both end up dying, especially if they're in the, well, only if they're in the early type B-type stars, you'll end up with two neutron stars in the binary system. And the result of this is that if they inspiral and they merge, this can be a source of gravitational waves that we can detect on Earth. And the majority of gravitational wave detections on Earth so far with our ground-based interferometers on Earth are inspiraling black holes, for which we have about 100 pairs or so. And we have a few binary black hole plus neutron stars and a couple of neutron star, double neutron star inspiring mergers. But as this is a burgeoning field of astronomy and more sensitivity is going to be available to us in these instruments over time, especially in the near future, when we begin to launch things like LISA, which is a space-based gravitational wave interferometer, we're going to be able to detect more and more of these weaker gravitational wave emitters than binary neutron stars, and particularly white dwarf binaries, which are intermediate mass stars in our B-class spectral type will be able to produce. So this is another important aspect of characterizing the binaries of our B-class. So for the black hole and black hole systems in particular, we want to know, well, how do these form? How are these systems? How do they come about in nature? And the main pathway relevant to our galaxy is that via mass transfer through Roche lobe overflow. So we've already talked about the Roche lobe and how stars can overflow them. And they eventually end up in a common envelope phase where we have a black hole plus black hole, or a black hole plus a neutron star binary. There are other pathways where you can get these double compact object systems, but this is the most relevant one for galactic stars. And we need observational constraints to be able to validate whether this pathway is correct. And one way to do that is to observe intermediate stages of this evolutionary pathway. In particular, in recent years, there's been a rush to find black hole plus massive main sequence stars, and doing this with different degrees of certainty, and that's something I'll talk about in a bit. So for stellar mass black holes so far, the ones that we've been able to observe, which is hard because they don't emit any light themselves. So far we have, as I mentioned, the 100 or so pairs of black hole plus black hole binaries that have been detected inspiraling through gravitational waves. We have X-ray binaries where the accretion disk around an accreting black hole is emitting X-rays, and we can detect these. But in most cases, these are black holes with low mass companions, and so these are likely to be the intermediate stage for black hole plus black hole binaries. And we also have, as I mentioned, several black hole plus main sequence stars, main sequence massive stars, that have been detected and studied to varying degrees of certainty through spectroscopy, and studying the motion of this massive main sequence star when it's affected by a companion that is as heavy and dense as a black hole or a neutron star. So ultimately, this thesis is asking a few different questions. It's asking what are the initial multiplicity properties of galactic B-type stars, so we can begin to provide better constraints for stellar population synthesis, for example. We have another question where if we have these identified binaries that we found in our first question, do any of them have compact objects in their binary systems? And then we can begin to validate these evolutionary pathways. And we also can ask, what are the observed rotational velocity distributions of galactic B-type stars? Because rotation in particular is a good signature of previous binary interaction, but also of the formation and of the future pathways of these stars. But where and how should we start looking to, for answers for these questions? Well, so far, in the spectroscopic domain, the binary fraction of B-type stars has been found for a couple of different ages and a few different metallicity environments. And it's important to look at both of these things because it's thought that they could have an effect on the formation of binary systems. If you have more metal content in a galaxy, or if that galaxy is older and you can see the products of binary interaction, for example. So this is largely incomplete, and while it does seem that there might be a decrease in binary interaction with age, more similar studies are needed to disentangle these effects. And that's where our cluster comes in, NGC 6231 in the galaxy. It's a young 5 megayear galactic open cluster, which should be good for detecting should be good for studying the immediate products of binary formation. And there's already a good indication that there are a lot of B-type binaries in the system, particularly through a few epochs of spectroscopy, where there was found to be a minimum binary fraction of 50%. And also there appears to be some pre-main sequence companions inferred from X-ray studies of the cluster. There also has been studies of the more massive O-type stars in this cluster, of which there are 16. And there is a minimum binary fraction of 63% on these. So it's a good place to start looking for binary systems. However, the binary systems in this cluster, the B-type systems, have not been constrained, as in we don't know what their orbits look like, and this is something that needs to be done. So how are we going to do this? Well, we want to observe a large population of stars efficiently, and we want to do this over a time series, so we can observe the different parts of each of these binaries' orbits, and we don't know what these orbits look like, so we just have to cover as much ground as possible. So what we do is time series optical spectroscopy, and we do that with the Flames instrument on the VLT, the Very Large Telescope, at ESO Paranal in Chile. And with this, we can retrieve the optical spectra of about 100 stars at a time, thanks to this fiber-fed multiplex here. So the result of that is us collecting 31 epochs of the spectra of 80 B-type stars in this cluster. And here's an example of one of those spectra. And the star is V star V946 SCO. It's a V2 main sequence star. And in it, you can see highlighted in green are the particular absorption lines in the spectrum that we are using for radial velocity measurements. And these radial velocity measurements are crucial in characterizing the orbit of a binary system. So to explain that, we can look at this movie where we have a binary system. We have the massive primary star in blue and the lower mass secondary companion in red, and the observer in green. And the observed spectrum we have is at the bottom, and over time what will happen is that the absorption lines in both of these stars will Doppler shift around their rest wavelength as they move towards us and away from us. And I'm sure most of you are familiar with the Doppler effect, especially if you have an ambulance driving past you in the street and it's like that. I think that's the way it goes down, yeah. So you'll begin to see common spectral lines, and in the case of a double-line spectroscopic binary, you can see both components contributing to the composite spectrum, but sometimes, due to observational bias, the primary star being much brighter than the secondary star, or the secondary companion emitting no light at all, for example in the case of compact objects, we can get single-line spectroscopic binaries, where we only have the signature of the more massive or the more luminous primary star to come on. So there are limits then to spectroscopy in characterizing binary systems. And these are limits that we need to take into account and model so we can provide a corrected binary fraction alongside corrected multiplicity parameters. So the first limit we take into account is that our campaign is only sensitive to certain configuration of binaries. And for example, one of the main things here is that our campaign lasts for 440 days, which might sound like a long time, but binary systems can have periods of tens of years, hundreds of years, thousands of years in some cases. So as a result, we only capture partial orbits of very long period binaries, for example, those that have periods of many years. And so we won't be able to properly characterize them, or in some cases we won't even be able to detect them as an RV variable. So as you can see in this plot here, where red is tending to 100% detection probability, and blue is detecting to 0% detection probability, then as our period increases past hundreds of days, and remember the duration is 440 days for our campaign, it drops off quite drastically for the kind of binaries we're expected to detect at, for example, 400 days or so. The other bias we need to consider is what we call the SP2 bias. And this is a result primarily of, remember I talked about two components contributing to the composite spectrum, absorption lines that are doing reflex motion around each other in our spectrum as we observe them over time. If these two provide equal fluxes to our composite spectrum, and this could be because they are equal mass binaries, for example, then it becomes quite easy for these lines to blend, especially at low radial velocities. They're not shifted that much, they kind of blend together. And as an observer, I'm only human, I'll look at the spectrum and I'll go, that doesn't look like there's two lines in the spectrum, that looks like there's one. So in that case, we do miss a lot of double-line spectroscopic binaries because of equal mass systems that have their Doppler shifts masked by a secondary companion. And you can see the result of that on the y-axis here, and especially towards equal mass binaries, our detection probability drops like quite a significant amount due to our masked radial velocities due to line blending. So we have our radial velocity variations from our optical spectra, and we want to find out which ones are variable and which ones are not. So we have our radial velocity variables in one bin and our non-radial velocity variables in another bin due to this variability criterion we use here. And then we want to separate the radial velocity variables into those that have their radial velocity variable because of orbital motion. These are binaries, we like that. We like the other things as well, but for this study, we want to find binaries. And for the radial velocity variables that have their RVs variable due to things like pulsations, where you have perturbations from the equilibrium in the star's atmosphere, and this causes that star to seem variable in RV to us. Alongside atmospheric activity and the stability of the instrument, all of these things can have an effect on the radial velocities we measure. So to cut these out and have stars that have their RV dominated by orbital motion, which are the binaries that we like, we put a rather arbitrary detection threshold at 20 kilometers per second. And it doesn't matter that this is quite arbitrary because this is used in our bias correction, and then we try and recover as many binaries as possible that could be under this 20 kilometers threshold in modeling for our observational biases. So the result is, after we correct for the observational biases, we have an intrinsic true binary fraction of 52%. And this appears to be, first, lower than the minimum binary fraction of the more massive O-type stars in the cluster. So we are further strengthening the case for a mass dependence on the binary fraction, which we did see before with the low and high mass stars. But when we compare them to the other spectroscopic surveys of B-type stars, both in the galaxy, in the large Magellanic Cloud, and in the small Magellanic Cloud, we see that it largely tracks with what we've seen before, which is a good thing. It is worth noting that Cygnus OP2 in the Milky Way, which we do compare to here, is not a stellar open cluster, but it's a stellar OB association, which is more gravitationally loose than a stellar cluster. And also in this study, where we have this corrected binary fraction, it does include 80 B-type stars, but it also includes 40 O-type stars. So this binary fraction here for NGC6231 is a good landmark really for a corrected binary fraction for B-type stars in our galaxy. So we found our binaries in our system, in our open cluster, and we can characterize these binaries by fitting their orbits with Kepler's laws of motion. And once we have constrained the orbits for these stars, we can begin to build orbital parameter distributions and compare them to other orbital parameter distributions of stars in different environments and of different masses and different ages, see if this has any impact on that. So here you can see the green shaded area is this duration of the observing campaign that I mentioned before. In red, we have the detection probability that we've estimated with our observational bias modeling. And you can see we're largely unbiased after 30 days, but you can see this detection probability predictably does drop quite drastically after hundreds of days. So we can compare our observed period distribution to other period distributions, as I said, of other stars of different masses and of different metallicities. And what's quite remarkable is that they all appear quite similar. And these aren't corrected for the observational biases, but all of these, or at least most of these campaigns, were designed specifically to be taken in a similar way. And so the observational biases should be similar for most of these campaigns as well. So what this suggests is that, well, if the formation of these binaries, the mechanisms of binary formation, has an impact on the period distribution, then we can suggest that there seems to be a general universality to the binary formation process, regardless of how massive these massive stars are, or regardless of what metallicity environment they were born in. So what do we learn from this first question? Well, we find that the binary fraction does suggest some mass dependence, definitely compared to the O-type stars. And we also find no meaningful statistical differences in the orbital parameter distributions to other samples of O-type stars and B-type stars in large matter-length cloud and also in the galaxy. So this suggests that there might be some universality to the binary formation process. So we have our binary systems, we have our single line spectroscopic binaries, which I described, and the double line ones. We want to study these single line spectroscopic binaries a bit further because of two things. First, if we characterize the unseen companions in there, we can potentially find lower and lower mass main sequence stars, so we can circumvent the limits of the original observing strategy. And secondly, we can investigate the possibility of companions that do not emit any light in the optical spectra. And yeah, so we suggest that these might be compact objects. We do this with what we call Fourier spectral disentangling. So we take a composite spectrum and we search for the signatures of a lower mass star in the composite spectrum. And in some cases, we're successful. We find several new double-line spectroscopic binaries amongst the SB1s. And we go down to a mass ratio of 0.1. Instead of in the original study that we did, about 0.55 or so. So we do extend our companion mass function downwards by quite a bit. If we don't find a signature of a companion in these single-line spectroscopic binaries, then we begin to investigate the possibility that there might be a black hole or neutron star in these binary systems. And in order to do this, the first step we need to take is to estimate the mass of the primary star. And we can do this by finding first the spectroscopic mass of the star. We can do this by doing atmospheric modeling of the spectra that we've already studied. And we do this by comparing our observed spectra along with ground-based photometry of the stars to both synthetic spectra, so models, stellar models, and also stellar spectral energy diagrams, which compare to photometry. As a result, when we combine the results of these two model fits for each star, we end up with our stellar parameters for each star, which are the effective temperature, the log G, which is the log of the surface gravity. We have the radius, the luminosity, and the projected rotational velocity of these stars, the V sine I. So from this, we can use the mass luminosity relation because we have the luminosity from these atmospheric fits, and we can find the spectroscopic mass. We can also find a secondary estimate of the spectroscopic mass by comparing our constrained stellar parameters to the position of each star on the Hertzsprung-Russell diagram, which I showed you earlier. Because if you remember, if you have the luminosity and you have the temperature, both of which are outputs in our stellar parameter fits, we can infer what kind of star resides there based on evolutionary stellar models on the Hertzsprung-Russell diagram. So as a result, we end up with two estimates of the primary star mass. Then we can use, on the top right, the binary mass function. So we have our two estimates of the primary mass, and we have our orbital parameters from our first study. And as a result, we can begin to find estimates for the unseen companion in this binary system. So we have 5 SB1s for which we couldn't find any signatures of a lower mass star in the composite spectrum. And as a result, we find the unseen companion mass for these stars with hidden companions. And the result is we find 4 of these have companion masses that are compatible with those thought to be for galactic black holes and galactic neutron stars. However, we have to also take the detection limits of our spectral disentangling into account. So this makes 2 of them kind of ambiguous cases, and the other 2 less ambiguous cases. We have 2 prime candidates really, V star V946 GO and CD411138. So in order to validate these candidates, we need to do more observations of these stars of different types, basically. So, for example, we can do far UV spectra of our candidates, and this has been proposed by another member of the team here, in the research group. And with this, you'll be able to find the signatures of strip stars, for example, which are binary interaction products, or are thought to be binary interaction products, where the envelope has been stripped from the star, and we can only see the very hot helium core of these stars. And so this will show up very nicely in far UV spectra because they're very hot. So what have we found from this question? Well, first we extend the companion mass function down to a mass ratio of 0.1 with 7 USB2s. We find 4 SB1s that have estimated companion masses that are compatible with galactic compact objects. And we find 2 particularly strong candidates in CD411138 and V star V946 GO, which was the spectrum that I showed you earlier. Finally, rotation is part of the atmospheric modeling we have done on DSB1s. And it's good to look at the rotation because it can have information on the formation processes of the star and how much angular momentum that they take from their natal clouds as they collapse. We have information on the evolution of the angular momentum transport in these stars, both for single stars in isolation as they spin up towards the end of their main sequence, but also the effects of binary interaction that can transfer angular momentum from one star to another. We can track this with rotation. And also, rotation can impact the nature of the end-of-life products of these stars as well. So what we do, as V sine I was a parameter in our atmospheric modeling, we can extend this to the entire sample, and not just the SB1s. So we have 60 single stars and 5 SB2s left in the sample. However, the stellar models that we use, the T-velocity models, they only go down to a temperature of 15,000 Kelvin, so we don't actually get to model the entire sample. So this is something that is pretty much preliminary work, and we need to use other types of stellar models that go down to lower temperatures. But for now, we have about 40 or so stars that we can place on the Hirschsprung-Russell diagram on the left, so luminosity versus temperature, and we have the effective temperature versus the surface gravity on the y-axis. And what's immediately apparent from doing this is that there is a discrepancy between the ages that we get from the stellar parameters and the reported age of the cluster, which seem quite young at 5 megayears. In fact, the stellar parameters seem to suggest that these stars are between 6 and even 30 megayears old, which would go against what we know about the cluster, which is that there aren't many evolved objects in this cluster at all. We would expect, as the cluster has a turn-off mass of 40 solar masses, which means any stars over 40 solar masses will have evolved of the main sequence. We would expect to see red supergiants, and we don't. So this is something that needs further investigation. And this age discrepancy also appears in the color magnitude diagrams as well, which is completely separate from the constraints of the stellar parameters. So this is just using ground-based photometry. And so whether this is to do with our observations, such as the precision of the ground-based photometry, or whether there is a problem in the constraints of our stellar parameters, or whether there is some uncertainty in input physics of the stellar models that we are comparing to, this requires further investigation. However, we can see with our ground-based photometry, we don't see a split in the main sequence that's predicted for populations of stars with stellar mergers, where you have hotter, quickly rotating merger products and cooler, slowly rotating non-merger products. We don't see this in the photometry, but again, this might be a result of the precision of the photometry, but also there might just not be any microtemperature points in the cluster. So yeah, this is something that requires further investigation with different types of photometry and different stellar models. However, the V sin i's, or the rotation values that we get, we do independently verify with another tool, and we deem them reliable, so we can still talk about them, thankfully. So we have here the rotational velocity distribution of the B-type stars in NGC 6231, and we have the presumably single stars in blue and the binary systems in orange. And you can see that presumably single stars tend to rotate faster than binary stars, which might seem counterintuitive, because well, there might be binary interaction occurring between binary systems that cause spin-up. And if the reported age of the cluster is correct, the young age, then we don't expect single stars to have spun up towards the end of their main sequence yet. So perhaps a fraction of the main sequence, perhaps a fraction of the single stars, the presumably single stars are actually binary stars, where we don't detect them as binary systems if they're long periods, and maybe they have particularly broad absorption lines because of this, and that's how we measure the rotational velocities through rotational broadening. Or perhaps there are binary interaction products in the cluster after all, and that's why we have these seemingly single stars which have been merged binary products. So this requires something, well, the resolution of flames is only a medium resolution of the observations, so this is something that might require more high resolution spectra. But we also compare our rotational distributions to those of other O-type and B-type stars, again, in different metallicity environments and also of different ages. So the O stars on the left, the B stars on the right, and the blue distributions are the NGC 6231B stars. And despite the appearance of some differences here, statistically speaking, there isn't actually much difference between these observations. But it does appear that B-type stars tend to have high velocity tails than the O-type stars do. So that's what we can take away from that. But we can also calculate the rotational critical velocity of these stars, the critical rotational velocity. And this is the rotation at which stars need to spin to break up. So it's basically their maximum rotational velocity before they end up, disassembling. And we can show our measured rotational velocities as a fraction of this theoretical critical velocity, or the maximum velocity. And it seems that the cooler a star is, so we have the temperature of our stars that we've constrained on the x-axis. The cooler a star is, the closer to their maximum velocity they tend to spin. And several are actually close to 80% critical. So this is either due to an overestimation of the V sin I, which is very possible, as we don't take a detailed account of the macro turbulence, for example, in doing so, in measuring the V sin I's. But also it could be the effect of, with hotter and hotter stars, you could have strong stellar winds as the stars get hotter, and these could take away angular momentum from these stars through the through the ejection of materials, through strong stellar winds, and such the ejection of angular momentum as well. So this might be a signature of that. But we also have indication here to challenge the claim that massive stars don't rotate faster than 50% of Earth, as we do have two stars in a marginal case here being massive stars due to their temperature that are rotating at about 60–70% critical. So yeah, by looking at our rotational velocities, asking this question, we do find this unresolved tension between our stellar parameters and the reported cluster age, which needs to be resolved. We don't find evidence of a split length sequence in this cluster by looking at the photometry. That could be caused by merger products. We find that presumably single stars tend to rotate faster than their binary counterparts. And we also find that the cooler the star, the closer the B-type stars tend to rotate to their maximum critical rotational velocity. So there is a few angles of future work that could be gone on from this thesis. We have auxiliary studies of other populations of B-type stars in our galaxy, and this is primarily one, to increase the number statistics of B-type stars in our galaxy, so we can get, for example, a more precise binary fraction, but we can also begin to find if there's any differences in similitudes between different populations of B-type stars in our galaxy. We also have the observational follow-up of the compact object companions to do. And as I mentioned before, this could be done through far UV spectra. It could also be done through interferometric observations to see if we can spot a secondary companion in these binary systems. So yeah, this is something that's very important to do. And thirdly, we want to resolve this discrepancy that we find between the models and our constrained stellar parameters, and the reported age of the cluster. And when we have these reliable stellar parameters, we can construct the initial mass function of this cluster and also the star formation history in this cluster as well, after doing evolutionary modeling using these stellar parameters. And this is useful because then we can begin to compare the star formation history of clusters in our galaxy with, for example, 13 Doradus in the Large Magellanic Cloud, and see what the impact of metallicity is there on that in particular. So yeah, I'll leave you with my summary. It's not very concise, but I want to thank you so much for listening, and also I just want to thank you all again for coming, no matter how far you came. I really appreciate it. So thanks for listening.
Thank you, Gareth, for this clear presentation of your thesis work. We will now proceed to the discussion of the thesis. And first of all, let me introduce the members of the examination committee. And I will start with those who are present here in the room. So we have the supervisors, we have Luc Sana from KU Leuven, we have Laurent Marie from the Royal Observatory of Belgium, we have Hans van Winkel from KU Leuven, and we have Andrew Tachenko from KU Leuven. And then we have two PhD jury members who are joining us from abroad online. These are Sylvia Tonen from the University of Amsterdam and Chris Evans from the UK Astronomy Technology Centre in Edinburgh. And how will we proceed now? So we'll have almost an hour of discussion time, and And we will start with the most remote members of the jury. We'll start with Chris Evans, so he can join us online.
Yeah, it's not Michelle.
Okay. So, if you're with us, you have the floor for 10 to 15 minutes.
So, afternoon, everyone. Can you hear me, Gareth? Is this working?
Hello?
Can you hear me, Gareth? Or
Yes,
the room?
I can hear you.
Yep, great. Fantastic. Thank you. So good afternoon, Gareth, everyone else. So thanks for your presentation, and sorry I'm not able to join you in person today. So first of all, let me just say a big thank you for sharing your thesis with us and reading through it, and just to congratulate you on the work you've done on these previously neglected B-type stars. I think it's a really important benchmark to have your results for the studies of these stars in our own Milky Way, and it gives us that study to compare with other populations. So it's a really nice set of results in here, and then searching for the compact companions as you've walked us through in your presentation. Just got a few questions, as you'd expect. So kind of just taking a step back, I'm glad you showed in your slides you had the plot from Mo and De Stefano about the increasing binary fraction with mass. So I wondered if you could say something about why do we see this mass dependence on the multiplicity? What's that telling us about the formation processes of massive stars compared to stars like our own sun?
Sure. I think there's a bit of echo if I talk Is that okay? Yeah, okay, great. Yeah, so with the mass dependence on the binary fraction, this could be suggesting that stars of different masses, binaries of different masses form in different ways. We have different formation mechanisms for the lower mass stars compared to the higher mass stars, and clearly some are more efficient than others. So for the low mass stars, I think that the main method of binary formation here is disk fragmentation, and this tends to form binaries at about 100 AU or so. But there is also the cases as you gain masses in the primary star that you can end up having different formation mechanisms at play. For example, you can have competitive accretion where you have these natal cores that are migrating around a natal cloud and all collectively competing for accreting this material from a cloud. And you can also have, for example, turbulence fragmentation as well. So this is a kind of similar principle, but these cores do not migrate around. They kind of form and collapse as natal cores in a dense molecular cloud quite separately, and so you get more you get binary systems that have higher separations. So I think my guess with that, maybe these latter formation scenarios can add quite a lot more binaries in these more massive stars than the kilomass stars.
And then you also, does that feed into the period distribution as well? In one of the plot, you had the other plot in your thesis alongside that, where you then see the great. It looks like you've got the more short period systems at the more massive end. So
So in that case, that does show that there's you get different period formation, different period distributions for primary stars of different masses. So this does indicate that there are greatly different formation scenarios for these binary systems depending on the mass. But as I've shown, maybe not depending on the metallicity, that might just affect the efficiency of these of the binary formation process. And it might, for example, in disk fragmentation, if you have low metallicity environments, you get less efficient cooling. And so you tend to form more massive companions. So maybe this is something that you'll see in the mass ratio distribution of these stars, for example, but maybe not in the period distributions.
That's a nice thought, and that links through to my next question. Given you teased us with your slide saying the potential universality of binary formation with metallicity. So in your thesis, you'd made the connection to the early universe and the elusive population 3 stars, and one of the motivations to study the lower metal systems kind of in the local universe. So yeah, just taking stock of your work, other work in the field, is that your thinking at the moment, where you're not seeing a strong evidence from metallicity, but then other factors would drive the population? Or
yeah, I think
what's the dominant factor, do you think, at the moment from what you've seen?
So, yeah, that's probably the most interesting result from that study of the multiplicity properties, is this very similar period distribution across most of them, and a similar eccentricity distribution. As I mentioned, with the mass ratio distribution, this is something that's hard to do, for example, with this sample, because we only have 5 sp2s. So it's very hard to compare a sample of 5 objects with, for example, more sp2s in the other sample. So I think this is something where studying more and more samples of B-type stars in our galaxy will help. So we'll have more sp2s, so we'll be able to compare the mass ratio distributions between these populations. But that does seem to, that's kind of where I'm going so far, is that, there does seem to be this similarity between the formation processes, regardless of metallicity.
Great, thanks. So just to pick up on what you said there about further follow-up in the Milky Way. So in the thesis, you mentioned programs or ideas of going to do big comprehensive studies in the SMC, as well as the new facilities coming along where we could do galactic studies. So knowing that telescope time isn't infinite, so if you had to prioritize one of those, would you go to lower metallicity or more comprehensive studies in the Milky Way, and why? Which one of those would you do first?
I think definitely lower metallicity. So we have areas like Sextans A, which is even lower metallicity than the small Magellan cloud. So we can continue to expand this axis of metallicity with these studies. Having more in the galaxy would be helpful, but I think this is something that we can also pick up in currently ongoing all-sky surveys, for example. Like Foremost will be studying the sky the southern sky 3 times over, and so hopefully we'll be able to get a lot more galactic stars from there. And so, I think the priority should be, lower and lower metallicity, and it's particularly because this also feeds back into, I think the study of low metallicity stars is a very important thing to do, especially as we can compare them with, for example, population 3 stars, and maybe the binaries within those population 3 stars at the beginning of our universe as well. So that's why I would go there.
Cool, thanks. And there's one last one for me, maybe at the moment. So you mentioned you went through these candidates you have from the, for compact objects from the SB1s, and you mentioned UV spectroscopy and interferometry. So could you say a bit more about what you would get if how would you narrow down or really confirm these targets, and what information would you get from these different techniques that would allow you to kind of pin a label on whether these are real compact objects or just hidden companions?
Yeah, sure. So as I mentioned before, UV spectra has already been proposed by Sikin. So this helps us to look at strip star, the potential strip stars in these binaries, and they will appear in the UV spectra because they have much higher effective temperatures than main sequence stars. So the flux ratio between strip stars and main sequence stars, especially in the UV, is going to be much more in the strip stars favor. And this is also, it's an exciting prospect to detect strip stars, even if it isn't a compact object as well, because these are very rare and hard to observe. So there's that with the UV spectra. As for lower mass companions, main sequence companions that aren't strip stars, I think this could be potentially be found through either higher resolution optical spectroscopy. So as I said before, we have medium resolution spectroscopy with flames. If we have high resolution spectroscopy, then maybe it becomes less likely for line blending to occur, and we have it becomes easier for the amplitudes of these absorption lines to be not much greater than the noise floor of the spectrum. So that would be, I think, also instrumental in trying to identify lower mass main sequence binaries that might be as candidates, but also interferometry as well will allow us to find, for example, main sequence or even non-main sequence companions at greater periods than those that we can probe with spectroscopy, which may be the cause of, well, these SP1 in particular, I think the max period is about 200 days or so, on the order of hundreds of days anyway. So maybe I'm not sure whether this is a period range that we probe with interferometry. I'm not too familiar with it. But it would definitely, yeah, I think that it probably would be able to discount some of the companions in some scenarios. Yeah.
Cool. Thank you. It's a good point about the high resolution. So if you could go back with another Flames program and kind of redo these observations, would you get any further information, or you really need that high resolution? Would you end up in the position that you still not have the information you need on these companions?
Yeah, so doing further Flames observations with the same resolution would still be helpful because, as we said before, we've got a duration of 440 days, and this was between 2017 and 2018 on this original observing campaign. And if we do more observations, particularly now, and they last, for example, another year or so, then we cover a time base of not only the original 2 years, but we extend that time base to, what year is it now? 2023. We're 5 years on, so we'll be able to maybe capture the orbits of those long period binaries that we don't get to fully characterize, and those that we don't even suspect to be long period binaries. We might have some that we've classified as non-variable, and they appear variable when we take detections of them now. So I think it still would be beneficial to use Flames, especially because it's multiplex, because more information is better on the stars that we have, and also, yeah, it's still useful, and still the range of velocity precision using this instrument is still good for characterizing these binaries. Yeah.
Great, thanks, Gareth. I think I'm probably out of time, so thanks a lot. Good to see you today. Hand over to Sylvia.
Thank you very much, Chris, for your questions. We'll move on to the next question round from Sylvia Tony.
Hi, Gareth. Can you hear me?
Yeah, I can hear you.
Okay. So first off, I really want to second Chris's words. So thank you very much for sharing your thesis with us and the papers, of course, because I really thought they were so interesting, and I was so happy to see them coming along. I think your work is really important, and it's impacting our group and how we set up our simulation. So it's really, well, I hope that you really enjoy seeing how useful your work is for the rest of the community. And so I, of course, also have a couple of questions. I hear a lot of echo. As long as you can hear me well, then we'll continue. Yeah. So my first question is about the orbital demographics. I'm so interested. Sorry, the echo is really bad.
Sorry, Sylvia, there's a bit of feedback. We could just try and fix it. Sorry, 1 second. Could I put the audio through this?
Microphone next to the this channel.
Okay. Okay. Sorry, Sylvia, if you could repeat the question.
Yeah. So my first question, oh, that makes it worse. My first question is about the period distribution. I think it was such an interesting result that you found that there were such large similarities between the O-type stars and the B-type stars.
Sorry, it's not happening. I will try and put the audio out of this, maybe. And then. Could you try again, Sylvia? Sorry.
Yes. So my question, I think that is this works?
Yeah, it works now. I can hear you.
Okay. Yes. Okay, great. Okay, so my question is about the period distribution that you found, right? And I think it's so interesting that you put it in context with the O-type stars and also with the different environments. So of course, O and B-type stars in different environments, and that you find such a striking similarity between them. And so the question that then automatically pops in my mind is, how do they compare to other types of stars, so A-type stars or lower mass stars? So is there a reason why you don't extend the discussion to that end, or is there a point in comparing them to A-type stars or FGK type stars, and how does it compare?
Wait, maybe I should unmute. All right, okay. Yeah, no, there's definitely good reason to discuss these things, discuss the lower mass stars. And as you've seen, well, as you haven't seen in the presentation, but I do include it in the thesis, the period distribution of low mass stars compared to intermediate and high mass stars tends to peak at longer periods. So periods around, I think they peak in about a year or so at most low mass period distributions. And also it's a different shaped period distribution as well to the massive stars. So as we find, like for example, the O-type stars can peak in around 30 days, so a lot of them tends to be in very close binaries, and what we see now with that slide that I showed, that most of them are in binary systems that are going to interact with the light color. It's less so the case for low mass stars, as we see, as I just mentioned, they peak in about a year. But also the shape of the period distribution is that we have a long normal distribution for low mass stars that tends to be found, whereas we have a flat period distribution found for the high mass stars. And again, as we were talking about with Chris, this definitely points to different formation scenarios that are involved in the low mass stars compared to the high mass stars. So while I may talk about a general universality for the formation of massive stars, as we see here in this presentation, this doesn't necessarily extend down to the low mass stars, as these are very different masses and they have very different. They might have different formation scenarios. So it's definitely worth discussing more. And again, as more and more multiplex observations and sky surveys happen, you're not only going to capture the massive stars, of course, you're going to capture the low mass stars, and this will help contribute greatly as well to being able to compare these period distributions. Yeah.
So that means that at some point there has to be a transition. The O and B type stars are showing like similar period distributions, and then as we move down the mass range, at some point it has to transition to wider, even if it's an abrupt change or a gradual change. Based on your data, can you say where that transition can be or cannot be? So for example, can you exclude that transition, or can you prove that transition has to happen outside of the B-type mass range, or can it happen at like the lower end, depending on your resolution, or number statistics? I think observational.
Yeah. So we actually, I think this is in the thesis. I don't think I have this in the slides. We do actually compare the early type B stars, so those that are thought to be massive stars, and the late type B type stars, in their period distributions. And here we actually do see a difference in the, I can't remember what that difference is, but there is definitely a statistically significant difference between the massive stars in our sample and the intermediate mass stars in our sample. So there is reason to believe that there might be this abrupt change in the B-type stars themselves. And so this is something that definitely could be explored further, because at the moment we have predominantly our sample is intermediate mass stars. So I think we have about probably like 40 or 50 of the 80 are the intermediate mass stars and 30 or so are the massive stars. And so if we have more samples of B-type stars, we can begin to increase the numbers of each of these mass beings and further see if there is this this transition between them. So I think that's still an interesting result of what we have. Yeah, is that we do see some signature of that transition already.
What do we need in order to pin that transition down? Like, if I give you as much money as you want, how would we set up? How would you set up your observations currently?
So the important thing we need is not just spectral typing, but we also need to characterize these masses through, for example, spectroscopic massing and atmospheric modeling to get the spectral mass. So it would be good to have the highest resolution spectroscopy possible, so we can be able to get, for example, better spectroscopic masses with our atmospheric modeling. So doing this for as many stars as possible. Yeah, I think that's kind of where we're at really. And what we want is to continue doing this for many stars in each of these mass ranges. So whether that comes in a higher resolution multiplex for to better constrain stars in a single population, because that can have its benefits as well, because we can have a constraint on the better constraint on the ages of these stars, because we assume that all stars in a stellar cluster, for example, are the same age, and so this takes some of this uncertainty as well away in modeling the stars. So yeah, I think that's where I go. Just basically more more observations with high resolution. I think of more stars as mass would go a long way. Yeah.
And you would still focus on young cluster environments, or do you at some point have to go to the field?
Look at older clusters for the intermediate mass stars, for example, because these do live, as we've mentioned, longer lives. It's just to have comparisons with the massive stars and you want to the same sample, then you would have to look at the younger clusters. So we are going to get, as a matter of the initial mass function, for example, we're going to get more intermediate mass stars as a principle of that. So if we want to get as many massive stars as possible as well compared to, yeah, looking at the younger clusters is the way to go.
And about this this possible transition, or at least the existence of wider orbit binaries, you mentioned in, I think it's somewhere in the beginning of chapter 2, maybe even the abstract, where you compare the binary fraction. So I go from the period distribution to the binary fraction, but of course that's kind of integrated over the full period distribution. And there you state that the binary fraction of B-type stars is lower than that of O-type stars. But I wonder, how does the selection effects, because I'm sure that you're not able to observe all periods, right? Every method has its ideal range of periods. How does that sensitivity to periods and the fact that these B-type stars may end up having wider orbits fit in with that binary fraction? So are we really sure that the binary fraction is lower, or is it just that the binary fraction at small orbits is lower?
Yeah, that's a good point, because our bias correction goes up to 3,000 days. So we try to account for all periods underneath 3,000 days. And of course, periods can be longer than this. I think one thing to say with that is that we are probing the stars that are bound to interact during their lifetime, because binaries with periods of between up to years, up to 10 years or so, depending on the eccentricity of these systems, are thought to potentially undergo binary interaction. But you're right that we could be missing binaries outside of this period range, longer than 3,000 days. And as we saw with the figure with, from Di Stefano, we are expecting, for example, for B-type stars in particular, it is expected to find 1.5 companions per star, I believe it was. And so we also need to have techniques that will better be able to construct those of triple systems as well, because we're not looking at a triple fraction, we're not looking at combined fraction, we're looking at a binary fraction. So further investigation into possible triples in the star, though we have looked at triples and tried to constrain triples in our cluster by looking at the residuals of radial velocity measurements, for example, and to no avail. Basically, we can't find any triple systems. Further investigation with that, for example, again, with high resonance spectroscopy to maybe find the signatures of triples in this cluster, perhaps would bump up, and instead of looking at binary fraction, maybe we could be looking at companion fraction in our stars as well, and this would increase the multiplicity again. So, yeah, using different modes of observation and also looking at triples would definitely, it's definitely not part of this thesis, and it's definitely something that should be discussed, but yeah, you're right.
I'm very happy that you bring up the triples, because that was actually going to be my last question. So you preempt me a little bit there. Smart, Gareth. Of course, I'm very sad to see that you didn't find any triples. And you mentioned a number of reasons of why that could happen. Can we draw the conclusion that maybe the triple fraction is lower, or maybe the third star needs to be much further out? How is it that you didn't find any triples while the O-type stars are so commonly in triples? Do you think this is, I think the observational techniques that you used are quite similar to the ones that were used for the O-type stars, right? So where do you think is the underlying reason for this? You're still muted.
Thank you. Can you hear me still there?
Yeah, again. Yeah.
Okay. So yeah, you're right in that. Yeah, we do expect some all those stars to at least be triple systems according to that diagram you saw. That diagram did include the other observational techniques I was talking about, including on-baseline interferometry. And the thing is with triples, or at least as far as I know, is that you can have a triple system in a stable orbit if the inner period is 5 times as short as the outer period of a triple system. So in that case, if the inner periods that we're observing, for example, peak at 30 days, for example, then if we multiply that by 5, we end up getting our outer periods being in the 150-day range, and we're already dropping quite significantly in our detection probabilities there, where we have about 50% or so at hundreds of days. So this could be a reason why we don't see triples in our sample, but again, the resolution of our instruments may play a factor into that as well. So whether it's a mixture of these two things, I'm not sure. But if I'm missing any other ways of searching for triple systems with spectroscopy, then I'd be very glad to hear it. But yeah, I was quite surprised as well. Yeah, that's what I'm at.
Yeah, it did make your analysis a lot easier, I'm sure.
Yeah.
I'll give the floor back to Katrien. I think my time is probably up.
Thank you very much.
Thank you very much, Sarah. We'll move on to Hans van den questions.
Thank you very much. First of all, I would like to congratulate you with your work. It's actually the work not only made it possible, but all the techniques that you use to come to certain conclusions, which are interested in the broader aspect of boundary and star inclusion. I do have a few questions, and one is about the observational bias. So you have your cluster, you observe it 31 times, and with previous answer to explain the time frame, of course, the length of the data stream is important, but you did not talk much about the sampling. So how, in your experience evaluating observational bias, is the sampling important or is the length of the order? So did you overdo with 21 observations or was it at the limit of what you did?
No, so the thing is, the alias is due to our sampling, which is where in the power spectrum there might be peaks in the frequency space where, due to the sampling, weren't too significant. And so I don't think 31 epochs was really overdoing it in this case. We also had a minimum sampling of a day, so there was at least one observation per night. There was a minimum spacing, though it wasn't always the case that it wasn't like 31 days, right? It wasn't 31 days in a row of observations. So that's also important to take into account because we do find rate of velocity variations underneath the day in some cases, and we're not able to properly characterize that. So we have a lot of rate of velocity variables underneath the day, and we don't know what the cause of those are without further investigation. So more high cadence techniques, for example, photometry, high cadence photometry will be able to kind of characterize those as well. So I think, yeah, I don't see any reason for 31 days to really be a downside in oversampling the 440 days. Yeah.
The reason that I ask is that in Thesis you have a table in which you have penalty control, in which you have not enough data to constrain the period. You have an estimate of the period, but it's not straight, and many of them are in the period range in which is red.
Yeah.
So I don't understand very well how you can have 100% detection cover. This detection cover means orbital, but not, and binary, correct? So binary signature is not enough for orbital.
Sure. I think maybe also this could be due to the eccentricity of those systems as well. I'm not sure whether those systems were highly eccentric. I'd have to look at it again. But if they were, then maybe they could have a significant period, but we're not sampling enough of a minimum and maximum of those rate of velocity variations due to an eccentric orbit. So that might be one thing, but I'd have to again look whether those were eccentric systems or not. But otherwise, yeah, I'm not too sure if they were like, because those systems were about 100 days or so. You said they're in the red area in this diagram. There's still a chance, right, that we couldn't properly detect them. It's about, you know, we end up with like 50 to 70 to 80%. It doesn't mean that 100% of them can be detected. So it might just be those fringe cases where we're unable to detect that, because our detection limit is 20 kilometers per second, and we might not be able to reach that amplitude with those. Yeah. Sure.
So I have to, so the detection probability in this case means not orbital properties, but the binary signature.
Yeah, so the detection is the probability of being able to detect that 20 kilometers per second rate of velocity shift. And we do that by, we simulate a population of binaries, so they're all binary systems in a sample that is the same number as our sample. So I think it was 80 or 90 or so. And we find out by randomizing the orbital configurations of these, the inclinations, and by using parent distributions that we take from studies of other multiplicity properties of massive stars like O-type stars, where we have a good idea of what the period distribution might be, what the eccentricity distribution might be. We use these as a parent distribution on these objects, and we see, as I said, we randomize those inclinations as well, and then we see how many we are likely to find this 20 kilometers per second on. So that's what, that's what the probability detection comes from.
And then another question, one of those objects that fall out of the range is one with very high amplitude, with very low period.
Yeah.
Would that not be an interesting object to look for a black hole?
Yeah, definitely. I think so, yeah. Yeah, so Do you remember how long the period was? Because I cannot. So it was probably the
10,000 days.
Yes. So again, that's like, yeah, it's 10,000.0. So that's a funny one. So it's clearly probably not 10,000.0. Yeah, it's obviously a very high. Yes. Yeah. So that definitely would be something to look at to see whether that is erroneous or whether, indeed, as you say, would be the result of having a very heavy object in there. Yeah, it's a So.
And another question. One more question. So you've done that with frames.
Yep.
And then we have a similar program on Harness.
Yep.
And in Harness, we don't have multiplexing, but we have a long time date.
Yep.
So what is the added value of having a longer time date? And is how can we optimize our observation strategy as to lower the observation bias?
Lower the observational what? Sorry. Bias. Okay.
What is these?
Yeah. So as you say, it's some of these auxiliary studies that I was talking about in future studies are being done with Hermes. We have 3 clusters there. So as you say, it doesn't have multiplexing, so it takes a longer time to get complete observations for this. And you only need a couple of observations to see whether something is radio velocity variable, right? And then you can continue from there and see whether you want to continue doing studies on these stars. That's why we've started on these programs, is by doing a couple of epochs of observations, seeing if they are variable, and then going, okay, we need to optimize our observation strategy then on these fewer stars with radio velocity variables. Again, this is not great either, because that RV variability could be a very long period. So it becomes quite tricky then to be able to optimize the observation time for large population of stars with an unbiased kind of, because you don't know what the auto configurations of these stars are going to be. So you really need an unbiased look at it. And that's why multiplexing is nice, because you can do all of those and do them at quite random intervals and still be an efficient way of observing. So try to be, that definitely does introduce more biases then, if you're having to cut down on the amount of stars you're observing. But the other thing then is that you are getting nice high resolution spectra as well. So it cuts both ways, where you're getting good spectra on some of your stars, but it does take a longer time. But then again, the longer time base is also good in some ways, because you're more sensitive to longer period binaries then. So what then is a downside, because it's taking ages to get in observations, then becomes an upside because you're probing a longer time base. So it's a balance of things, really. Yeah. So.
Thank you.
Hey Gareth.
Hi.
I just realized it's the first time I'm in the jury of my former
This is just how I remember things.
Congrats on this wonderful work. And thanks a lot for a very nice presentation. I enjoyed it very much. So at your largest convenience or inconvenience, I decided to ask a question that you will trigger today. Not only Thesis, not only at home. So they will perhaps be a little bit naive. At the very beginning, maybe slide 3 or something like that, where you show the progressive diagram with the Yeah, definitely. So that sequence, O to M, we've been referring to those guys as stars constantly throughout your talk. What are those whiteboards actually? And neutron stars you also mentioned. So what's the definition of this star? What are the whiteboards? How should I understand?
So, I'm going to say, well, I've been mentioning these main sequence stars. So these are fusing elements in the cores of their stars. When you're reaching things like white dwarfs, you don't have fusion in the cores happening. So that's why we're ending with these stars being these inert objects So you could refer to them as like stars, I guess, if you want to, but I see them more as like end of life products than stars. So that's why these are, whereas in your supergiants and your giants, you still have fusion happening in these cores as well. So yeah, this would happen in those, and again in neutron stars, you won't have that as well, even though they are called stars. So there's a lot of nomenclature there, but yeah.
Are you suggesting that we should drop the word stars from neutrons?
Yeah. Neutron things.
Yeah. Second naive question. You showed us a graph, not this is a function of sum and mass, right?
Yep.
Where you convey a message that all the four are stars, probability binary. How would you check if our own star is actually binary? Is that
How do we check if our own star is in a binary system? Well, we'd be able to find our own motion with respect to other objects in the sky. So we already have to correct for heliocentricity when we take observations of, when we take radial velocity measurements of distant stars, for example. So we have this barycentric motion that is the motion of the Earth around the Sun. If this, where you had the Sun then orbiting around another star, I think this would come up residually in those barycentric corrections. That would be my guess, really, because it's not like you can point a telescope at the Sun and then go, okay, we've got this radial velocity from that star orbiting another star. So I guess it would be from the reference frame of other observations, other objects, that you'd be able to tell if we were part of a binary system or not. Yeah.
okay? Let's take that as a must. One more question. So you mentioned that the future of gravitational wave detections is by taking the instruments to space.
Mm-hmm.
Could you elaborate a little bit on that? Because in my understanding, these instruments need very high stability. How can you guarantee that in space? And what's the advantage of taking it into space?
That's a great question. So as far as I know, I'm quite unlearned on these things, but as far as I know, LISA is the triangulation of 3 satellites that are that have lasers pointing at each other, and then it's analogous to the ground-based interferometers, where you have the constructive and deconstructive interference of these atoms moving between the points of the interferometer. So I think the problem if you do that on the ground is that you need a very stable, you need to account for seismic activity, you need to account for cars that are driving by, all these things. I think in space, if you manage to get a very stable orbit between 3 satellites, I would not tell you how to do that. Luckily, I'm not doing that. I think that you could circumvent those things quite nicely if you had these things stably orbiting. I don't even know. I imagine it's orbiting in as a normal satellite would around the Earth. And then you're missing this seismic activity that's happening. So yeah, that might be an answer.
Okay, thanks. And very last one, maybe more serious question to pick up on the one that Chris asked. So you explain us that there are different mechanisms for binary formation.
Mm-hmm.
Is this good enough for us to know that there are these million options, or is there any point in figuring out which one dominates? And if the latter, how would you do that? What type of observations maybe analysis will you answer that question?
Yeah, so it's definitely something that requires further investigation, and it's very difficult to observe star-forming regions. That's why we have to take all of these inferences and gas layers, because star-forming regions have a lot of dust and gas, and they obstruct a lot of observations of, especially massive stars, which remain in their natal clouds until they reach the main sequence. So definitely infrared observations of star forming regions and binaries that are forming within these, and in particular, even the outflows that result of certain configurations of binaries forming. Observing these kind of things will hopefully provide a lot of information on different formation scenarios, so it still is worth looking directly at the source rather than just inferring on final products of binary formation. So it's definitely something worth doing. Yeah.
Thank you, Andrew. And I'll now pass the mic to the supervisors. Laurent.
Hi.
So, very nice work. I think you did great with your presentation also today. I think I had the time to ask you all the questions I had on your thesis. I might have more, but given the time today, I will skip them. And
I'll follow the advice of Laurent.
It's always good to do.
It was a very good advice actually. So nice work today over the last few years too, with questions and answers on my side.
Okay, yeah, and I, as the chair of the committee, I also want to congratulate you on a great presentation today. Nice question rounds. I have a few questions, but in the interest of time, I will keep them for afterwards because I want to open the floor to the public. Are there any questions in the room? Yes, great. I saw one here.
Thanks a lot, Gareth. Yeah, I'm very impressed by this work. It's really good job. As you know, I'm very much of a peanut star guy.
We all know this.
So, how is it? You haven't found any peanut stars in your sample, or could we try and find some of these B peanut stars somewhere else?
I would say probably because, well, if we believe the age of the cluster to be correct, which again there's some tension over that, so I'm going to say it's young for now. Then perhaps there is not enough time for these open contact systems to be formed. So that's probably the main reason. But whether there is some difference in the period distribution between we haven't seen the difference between the period distribution between the B and the O type stars, but we don't know for certain how many of these are going to end up in systems that are close enough to end up in open contact systems. So maybe in the future we'll be able to tell us certain, or if we observe these objects directly.
No.
But we don't see them. Yeah.
Hi, Gareth.
Hi, Don.
Good talk. Well done.
Thank you.
You mentioned pulsations. I'm going to ask you about that.
Oh no.
So you have this fantastic data set which contests a hypothesis that's been made in the literature recently, such that pulsation fraction increases within clusters compared to field stars.
Yeah.
So you have this multi-epoch data set, but of course you're going to throw away potentially partly variable stars from the binary sample. Do you think you have the data to answer that question compared to the field stars?
It really depends because first of all, I believe that the pulsations don't necessarily have to be periodic, right? So whether that's something that we have a lot of stars that we deem to be periodic but not significant radial velocity variables, as in over 20 kilometers per second. That's why we have these two bins. Also, if you do have high resolution, then you are able to see the effect of pulsations on the actual structure of the lines themselves, and that's something that we can't really do with the flame spectra, I don't think, because it is too low resolution to see the effect on the core and the wings of each of these lines and these pulsations. So that is interesting. I want to ask you why that would be the case in clusters as opposed to field stars.
We don't know.
Yeah, that's very interesting.
From photometric studies, that seems to be the case. I'm just curious because
Yeah.
the bright stars that you're looking at, terrible to look at with things like tests.
Yeah.
But the RV data might reveal the same.
Yeah, sure.
I'm curious if you looked at that.
Yeah, so that isn't something that we've gone into. Of course, yeah, we've looked at them. It's like by project that we don't want to look at. So it definitely, that would be valuable to have a look at and see if there is any correlation to that and see if there's any truth to that, because that is very interesting.
Cool, thanks.
Thank you. Any last question? If not, then we will go and deliberate. We will be back before. Ladies and gentlemen, dear colleagues, dear Gareth, I now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Gareth Banyard has presented to the faculty his PhD thesis on the topic the multiplicity of B-type stars in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Gareth Banyard the degree of Doctor in Science, Astronomy, and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described by the ALIA, European Code of Conduct, reliability, honesty, respect, and accountability. And with this, I close the official session, and I will, well, actually, I have to hand you the signed documents as a proof of you obtaining your PhD. You'll have to sign yourself as well. So this is your certificate. You can do that later on. So we do it now? Okay. So, sign to show that you agree.
I should know.
2nd of October. Yes, okay. And then now I will pass the mic to
Well, Gareth, Dr. Gareth, oh, I'm not sure I'm going to stand there because otherwise I feel smaller than I am. And that would be the first time in 5 years.
This feels better.
But now here that I'm standing on the same floor as you for the first time, I can address you as my equal, as Dr. Gareth Banyard. So this is very nice. Let me go back a little in time. The position that Gareth was offered as a PhD student was actually offered to somebody else. I believe Gareth knew that. But that person failed on us. And so we had to reopen the position, and the interview was with John Sundquist that couldn't be here today, if you remember. And we had a nice chat with Gareth, and then we closed the Zoom session, and then John and I looked at each other and said, well, our problem is solved. We find a good candidate. So actually very happy that this happened and that we didn't fail this, not within a few months after offering the position, but also in the next 4 or 5 years. You've been a steady person on which we could always rely. Maybe you didn't mention, but you have analyzed accounts what 31 times 75 objects, so that's a few thousand spectra. I think it's a lot of work. You've also organized observing campaign with the Mercator, following the exact same strategy to gather. You mentioned 3 clusters, but I think there's a 4th one that we copy your work and that we're continuing on this. And that has been a topic for master thesis actually this year. So this is all contribution of Gareth to this institute and to this research field. In terms of techniques, you did normalization, Gaussian velocity, variability analysis, binary detection, bias correction, orbital fitting, period search you need to. You measure temperature, gravity, projective rotation, luminosity, you use spectroscopy, photometry, and lately we've been talking about X-rays. So just covered a lot of ground, and especially you establish a methodology that we tested and tried, and we can now deploy it very efficiently because that mass of students copied your methodology and was able to do 4 clusters in 1 year, while it took you 4 years to do 1 cluster.
Wow.
But she didn't do the part of the research, developing and testing the methodology. We could just deploy it. So that's the advantage. Well, I forgot to mention, you've been studying stars that you could see, but also in your second paper, you studied stars that we couldn't even see, right? So that's also something that we've developed with you and with the team, is that there is information in things that you don't see. All right. So it would not have been possible to cover that much ground without facing a few challenges. I think that one of the first challenges that you had is that maybe you were surprised to get the position, maybe you thought that you didn't deserve it at the beginning, and I think that this is a feeling that sometimes comes back, but clearly what you've demonstrated today, what you've achieved with your manuscript, and the many discussions that we have had with Laurent and myself, we are very confident that that's a feeling that if it comes back, you can just kick it out and then ignore it completely. There's been COVID, of course, that has been a tough one. There has been the lockdown, and then also you got COVID, and that has been a tough on you. This has been on the people, but you get over it, you rebound. And probably the biggest and most difficult challenge you've been sharing an appointment is Callum for 4 years. But you did it all of that, right? So it's been very nice to be in the team. I've said many meetings, and we've been discussing a lot with you in the last 5 years. And there's a few things that I've all been pleased from your work attitude. It's the no bullshit approach. If there's something that you don't know, you just say you don't know. If there is always a good questions, because Laurent and I, we always have a lot of questions, things that you did yourself, you could explain them. You knew exactly what you did and why you did it, and those 2 qualities, I think, are great qualities of scientists, and we got to know about society today, and we've seen that there is an addition in the declaration that scientists today is something that the society needs, and so you definitely have proven and demonstrated that you have those qualities. There is something else that I wanted to add as a last thing, is that indeed some of the part of the work was slow as it is in research, but the deliverables that you gave to Laurent and I usually require very few iterations. So the quality that you delivered was immediately good. And I think that in a sense it's another way of working, that some of the students that try to give an answer as soon as possible, but you need to tell them 5 times that that answer is not correct. With you, it was not the case. The majority of the times when you were delivering work, which Laurent and I, we were looking at it and say, well, that's nice. We can build on that, and then we're continuing, right? And that's one of the reasons why you've been able to touch so many topics. It's because of the fact that we did not have to iterate so many times. So I'm going to stop there. I actually have a present that I left it upstairs, and it's actually only half of a present because I wanted to give you something else, and then I realized that while you learned a lot of things in the last 4 years, you didn't learn Dutch. Which I wouldn't say it's a bad thing. But then at the shop, then I realized that the present I had in mind would not be suitable, and I had to order it online in English, and then it was not arrived yet. So if I see you before you leave, I will give it to you, otherwise I will ship it. It's going to be a little souvenir from our time. So Gareth, congratulations. Laurent, you want to say a few words?
So Gareth, again, congratulations for the
I mean, these 4 years were rich in many senses. And after the COVID, you also found the strength to go beyond that. And I think that maybe something that you should also be proud of. Because I think the deliverable that you provide us was very good. The thesis, but also today, you showed that you touch many things, like as you mentioned. So again, congrats. I enjoyed the time that we shared together during these 4 years, working, learning each other several things. I learned the Gareth during the day, and I think the most memorable thing that I can remember was also Gareth during the night at the Edinburgh. Those who know that can testify that. So it was very nice, and again, all the best for the future. Sorry.
Yeah, thank you so much, especially on that illuminating last sentence. Yeah, I just want to say, I mean, I've obviously acknowledged in my thesis how much you guys have helped me throughout the last 5 years. I just want to reiterate that. Like, I would not be here if it wasn't for your patience and just how well you've treated me over the last 5 years and just your general advice. So I want to thank you very much for that. I do have some gifts, I think, somewhere. Mother. Over here. Thank you so much. Unusual shape of that. No idea what this is. Just a token, thanks. Yeah. Wait, so is this the last bit, right? Session's closed. Yeah, I won't do a big speech. This is what everyone says. Well, I won't do a big speech. Because I want everyone else to stop drinking. So I'll say that as well. But yeah, again, I just want to thank everyone who's, especially people who made the effort to come here from far away. Like, I don't know, it means so much to me. I thought of it, right? Excuse my language. But yeah, thank you so much for coming. And I'll see you. We have a reception in the Stuck Cafe, which is in this maze of a building. You go down to the reception and up the stairs. So we'll have a reception there. So again, thanks everyone. That's it.